So with that, I'll just hand it off to Shekufa. Good luck.
Thank you. Hello, everyone. Do you have my screen?
Yes, I see it.
Okay. Hello, everyone. Good. I hope you're all doing well. In this session, we'll take a look at tensors and autograd, and we will get into more details about these concepts. And also we will take a look at the exercises in your assignment file. But before that, we will make a quick review of all the materials that you learned on Wednesday. Okay, as you might know, the common data structure that PyTorch use for storing the numerical data is the tensor. Tensors, just like and the arrays of NumPy library, can handle and work with multidimensional arrays, but in compared with NumPy arrays, tensors
Shekufa, you're kind of breaking up. Shekufa. Shekufa. Your audio is breaking. Shekufa.
Okay, fine. Because she cannot present, maybe I can handle it.
Okay.
It is just a internet problem. I know about that. Okay. Okay, fine. Let's take a look at the tensors in the PyTorch. First, we can start with the data structure, tensor data structure. That is pretty similar to the NumPy arrays, and also we have different types of kind of data structures in other packages, but in PyTorch we usually focus on the tensors. We can say that we have different types of just the tensors, they have a different kind of dimensions. We can start with the scalars, which are just we call them zero-dimensional, just scalar, like the regular variables in Python.
Sorry to interrupt you, Kayan. If you could please share your screen.
Okay.
Yeah, that would be great. Thanks.
I think I'm not able to share it.
Oh, okay. Sorry. Okay, now you can.
Okay. Just make sure I'm writing. Now, can you see my screen?
Yes.
Okay, fine. And then, okay. Another point is that if you want to ask a question, just you can unmute and ask, or just ask it in the chat. That's fine. My friends can answer the question. I will take a look at it later. Okay. So we started with the zero-dimensional or just scalar values in PyTorch, which is very similar to the other regular variables in Python or other programming languages. And also we have a one-dimensional tensors, which are just the vectors, and the matrix or arrays, which are two-dimensional, and also in we can say that in NumPy, when we can handle all of these types of all the dimensions, but generally in mathematics and also in programming languages, when we have a three-dimensional arrays, tensor arrays, you can say arrays, and also if it is more than 3 dimension, we can call them tensors. So it is generally for the 3D, 4D, and so on. But in PyTorch, we only have one data structure, which is just tensor. It can be 1D, 0D, 1D, 2D, and so on. Okay, this is about the tensors, and you can see the kind of the structure of the tensors when they get complicated when we have more than 3D kind of tensors. Okay, but you can see the structure of the list just as a reminder how they look like. It can be a kind of 1D tensor right now for the variable called a, and then we have 3 values. You can print and change the values, which is run the code from scratch. So okay, so and also this one. So in the lists, you when you have for example, here you have 3 values, and you can change the values by indexing the variable which is named a, and it is pretty easy to see the whole list together when it is just 1D. We can create multidimensional arrays also using lists, but we are focusing on tensors, and as the same structure that we have here for the list, we can have something like first an array with 3 values, which is all ones. And then if we want, we can change the values exactly like we did in for the list. So it is kind of pretty similar. We are not worried about that one. And also in the list, we can just talk about the differences between the structure of the saved values in the RAM. You can see that in the list, it is just distributed over there. It can be distributed over the RAM. We don't know where are they, but they are just accessed like different or just separated values for each index inside the list. But for tensors, or especially for the NumPy arrays, which are similar, they are organized in a special way. They are all saved together like array, which you can see on the right side of the screen. It is, let's say that it is not that hard to just find the locations. And this is just the view that you can see in the memory, but basically we save them as a vector, kind of. If no matter if they are 2D, 3D, or just multidimensional arrays, we just save them. They are serialized and they are saved in like a vector inside the memory. So, okay. I just wanted to give you a view about the differences between saving lists and tensors or NumPy and the arrays in Python, which are different. And also about the indexing. As we did in Python for NumPy arrays and for lists, for tensors, we have the same strategy. If we, for example, here you can see a list, some list, and if we want to access all the elements in the list, we just use a column. And then let me run it first, and you can see. So this is the first line of code for which is printed, this one. And also we are printing the whole list altogether. If we want to access some elements, for example, here from element 1 to 4, which 4 is not included in the printed array, which we have, this is the whole list. So as you can see, we excluded 0, and we have 1, 2, and 3, and 4 is not in the O2. And this is the general format, which is instead of three values. The first value is the starting point. Which value do you want to print? So it would be included the end point, the last element, which is not included. So we just start from start to end -1. We will print start that element and continue until we reach end, but end is not printed. And we have the step size, which you can see here, the last one. We start from 1 to 4, but the step size is 2. So instead of 0, 1, 2, 3, 4, 5, we start from 1, and then we are not printing 2 because the step size is 2. So 1, 3, it could be 5, but we end at 4. So it is just 1 and 3. And okay. We created the points here, which is the tensor. I could just give you a better view this way. As you can see, it is a two-dimensional tensor. So again, run it. And if I want to just, okay. If I want to show you the indexing in tensors, it is pretty the same. So you can see I printed the whole tensor and also index from 1 to n, but to the end. And because it is 2D array, when we use just one index, we can have 2 of them like this. So when it is just 1, I mean that I just want the rows, not the columns, because as you can see here, I have 3 rows and 2 columns. Okay, so in this case, with one index, I just access the rows. So the whole array is this one, and the second one for 1 to the end, I just remove 4 and 1, or the first row from the printed version from the O2. So 5, 3, 2, 1. And then for it is exactly the same thing. These lines of code are the same. So, but this time I just say that I want all the columns by specifying just a column instead of directly mentioning the columns. It could be something like from 0 to the end. It's the same. And also, in this case, I just say I want row 1 and then column 0 from row 1 to the end, and then column just 0, as you can see the output here. Right? No. Okay. Oh, this is the output, which I have 2 rows, but I just print out 1 column, which is 0. And then if you want to add another dimension to your array, you can use this notation. But we have a method which applied to the tensor. So it is on a squeeze. And these 2 lines of code, again, they are doing the same thing. But usually people use this notation. It is much more clear. And also you can add the dimension to wherever you want. We have a 2-dimensional array, so you can add the dimension to the end, which can be -1, to the last dimension, or to the first dimension. And as you can see, instead of 2 open brackets, we have 3 of them now. when we do use the unsqueeze. And if you want to add more dimension, you can just use unsqueeze again. Applied and dimension is equal to 0. Okay. Oh, what happened? Make sure everything is right. So now we have 4 of them instead of 3 because we had originally had 2 of them, and we added 2 functions on the top of the 2 method as the top of the array, and we have now 4 of them instead of 2. So we added dimension, but in this case, it's the easiest way. If you want, just add 1 dimension to the dimension of 0. So it would be just using null and bracket. But we can talk about the data types. We talked about the data structure. And then for the data type, it's kind of similar. We have torch.float 32, 64, 16. And we have some shortcuts for them. Here for the float 32, we have again float and double and half. And for the integer, from its 8, 16, int 32, and so on. And here, integer data types, we have shortcuts, which is short, int, and long. We usually use this format, easier and also here. But if you want to you can use each of them. And also we have torch.uint. You can see that most of the images, regular images, are of type uint8, which the value is an 8-bit integer. The value that can store can be between 0 to 255. And also we have the Boolean, and they are all saved inside the torch package. Oh, okay. But for casting data types, we can use different methods. For example, here we have a array with 10 rows and 2 columns, which are the values are 1. But the default value, I think it is to float 32, the default value for this function. And we are going to change the d type as we create we call this constructor and we create the array. So it would be the d type is equal to torch, for example, dot double. Instead of float 32 or torch dot, instead of torch dot float or torch dot float 32, I am going to change it to the torch dot double. And also when we want to create a tensor, kind of manually create a tensor, we can still just directly mention the d type and change it, cast it. And we can see the d type this way. When we create when we have the tensor, we can just mention the d type attribute, and it says that what is the d type of the short points, which is torch int 16. And you can see that we use the shortcut here, torch.short, and also here we have torch int 16. But there is another way for this. For the d types, you can use, instead of saying, let me add another line of code here so I can show you all 3 types here. Type. So in this case, for example, I don't know, torch dot again flow, something like this. So as you can see, we can change the d types, cast the type using the method double and short. We have exactly as I told you here for this version, for the float, double, half, short, int, and long, we have the method for casting. So you can directly say double, short, I don't know, or other ones. And also you can change the data type using this method, which is that type, and then just we can mention the d type. There must be a func, there must be parameter name. So here, yeah, you can see. So there are 3 different types which are easy to use. And also there is another method which is called to. If you want, you can just change the data type using to method. Okay. Double, short, and so on. So like NumPy, we have different kind of APIs in PyTorch. And we can use different methods for, I don't know, for changing the dimension. It is pretty easy. We have mathematical functions again in PyTorch. I'm not going to just describe all of them. We have random functions, which is directly accessible using, for example, torch.rand and torch.normal, torch.random rand int, or something like that. And we are going to check some of them, but we can load and save all the tensors, which is pretty easy. I'm sure that they have been covered, and also you will see them in the next workshops. Maybe you will work them directly for saving models, saving tensors, and loading them. So they are pretty important to know about them. But about moving tensors to the GPU, the only kind of the main difference between PyTorch and PyTorch tensors and NumPy array is that you can just calculate whatever that you have using the tensors on the GPU. And it is really, really easy to work with, just one line of code. If you want to just move your data from the RAM, from the CPU, and run it on the GPU, you can use the to function as we saw it before for casting D types. Now, in order to change the device, by default, they are on the CPU. So if you want to change it, you can just mention that device is equal to CUDA inside the to method. So you create your tensor, and actually you can just say points, for example, as our tensor dot to device, and it would be on the GPU. And from this point, whatever that you are doing on the GPU, it would be done on the GPU, not CPU. And for heavy calculation, mathematical calculation, usually tensor based, is for just it is really, really fast compared to the CPU. But you must be able to first send them to the GPU, because when you are doing the calculation, both of your I don't know, if you want to multiply two tensors, something like this. Let me copy and show you. For example, if you want to multiply two tensors, both of them must be on the GPU. So it would be just easy to send them to the device and then do the calculation. Okay, so in this case, there are two ways to do it. When you create the tensor, you can just send it using by mentioning the device, which is here is CUDA. If you have only one GPU, you can just say CUDA. If you have more than GPU, you can say, okay, I want to, for example, put it on the GPU numbers 1, the first GPU, or 1, 2, 3, and so on. So easy to say which device do I want to work on. And also you can clearly mention the D type, which must be float 32 for the GPUs. Nowadays, GPUs support float 16 or short, but it is always better and safer to just mention the D type this way, because we don't know the original D types of the tensor. So it's better to say float 32 or float for the memory, for the D type.
Sorry to interrupt. I just want to say, like, we're at the halfway through the assignment mark. So if you would like to go over the exercises and just kind of like speak through this stuff, like, it'd be a good time. Yeah.
Okay, thank you.
Nice.
I will do. Yeah, and also, so this is for the device. You can just send it to device, and there is another way which you can directly mention the I want to send it to my GPU. So you can say that CUDA or CUDA and the number assigned to your GPU 0, 1, and so on. And also, if you want to move back to the CPU, you can just use that CPU or 2 points.2, and here you can say CPU. Okay. Okay, you can run it from here. Nope. You can see that I have error because I don't have GPU device here. So that's the main reason, but that's fine. Maybe I can open it in the drive. But for the the first exercise is just about creating a grayscale image and work it on the using the tensor. So I can just directly go to the solution and check it one by one. So I can first mention the exercise. The main purpose is just working with the images and also in the format of tensors. And we will work with the data type, and also you can see that it is pretty similar to the NumPy arrays, and you can see the channels, how we manage the channels in PyTorch. Okay. The solution for this one is just here. So okay, sorry. I just want to send it to the drive in case I am using it there. So for the image, we can create a random image, or you can just open an image if you want. And in this case, we think that we have an image, so we load the image. Uncomment this one. You can see that we use PIL library in Python to open the image. And when we want to convert it to the NumPy arrays, we just use the function np.arrays and give it the loaded image as a parameter. And then when we have it is going to be a NumPy array, and the kind of last channel, if it is colored image, it would be last channel image. I don't have the image here, but I'm going to use the random version here. So it is pretty the same. When you have the NumPy array, it would be easier just to work with. And also, you can see that if we have a NumPy array and we want to convert it to the torch tensor, we can use the function from NumPy. It's the built-in function in PyTorch. So torch that's from NumPy and image. We can cast the dtype and also change the kind of dimensions, transpose it. There are two functions. One of them is transpose, the other one is permute. And in this case, I just say that I want the last dimension, which is my channels within the channels of the image, to be the first one. So it is permute, and the second dimension, the first dimension, the 0 dimension, and kind of dimension 1. So I just reorder the dimensions. So instead of, because in PyTorch we need to work with the last channel images, not the first channel. That's the main purpose. And so, okay. So here I start with the random function, random normal, and create a first channel image, which the dimension is the channel, the height, and the width. And I clearly mentioned the the D type to be float32 because maybe we want to work on the GPU, so it is safer. And also in this case, when you want to convert it to the grayscale, we can use the mean method for that tensor. Now I know that this img variable is containing my image, but it is just a tensor for me. There is no difference between a tensor and image for PyTorch. So if you want to just calculate the grayscale version and have a kind of one channel or just 2D dimensional tensor, you can use the mean function. And then print average dot shape. So we can see that this is 2-dimensional, it is not more than that. And then so but let's see. In this case, we want to just work with the images and see the different calculations. We converted it to the grayscale image, and here we calculate the weights. So for the weights, it is because I only have 3 channels here in the image. I could say I only need 3 values here. For each channel, I need 1 value, channel 0, channel 1, and channel 2. And the D type is float32. These are my weights. And also, as you can see, let me show you the original shape. Shape. So it is 3 by 256, 266. So in this case, it is a 3-dimensional array. And if I want to multiply both of them, and I want a weighted version of the image, I need these weights to be 3-dimensional, but originally they are just a vector 1-dimensional array. So as I showed you, I squeeze them twice, so the shape would be the shape would be 3 by 1 by 1, and it means that for each channel I have 1 value here, and if no matter what, it would be just resized by PyTorch itself for the multiplication. And then I can do the same, calculate the mean with the, here we just say which dimension do we want to calculate the average of the channel on. So we want to calculate the mean and remove the first dimension, which the shape at the end would be the same as before. But this time it is a weighted version, converting image to the grayscale. Oh no, dot shape. So here you can see it is the same. And also, okay, and about the just calculating everything on the GPU, you can say that I can first define the device, that if I can use the PyTorch to check that if I have the GPU available or not. If there is GPU, this variable would be CUDA, else it would be CPU. And then the same thing as before, unsqueezed weight, which is just this version of the weights, and I will send it to the GPU. And then if the GPU is available, I can just perform the multiplication here on the GPU. If not, it would be on the CPU. Let me run it. You can see that because I don't have GPU, it is on CPU. But if you have GPU, it is pretty straightforward and you don't need to do something. Just, you can see, send both of them to the GPU and it would be run on the GPU. Okay, and you can see that device using the attribute.device. Okay. I have another version here, which you can see the result. So if you have GPU, it is just on Google Club. That's why I have GPU here. And then you can see that I just run the same cell, but you see that the result is on the GPU. The calculation is going to be on GPU, and I have only one kind of GPU, so it is just CUDA index 0. See, this is the result. I can run it again if you want. So it is the same. Okay. So if you have the GPU, it is the same, just 2 lines of code which you send it to the device. That's it, nothing else. And if always, no matter if it is on the CPU or GPU, if you want to check the device, you can do it. And when I want to bring it back to the CPU, I can use the CPU function. So here at the end, you can see that the device is just CPU, not GPU. This line of code is for this print function after I moved it back to the CPU. Okay, you can go back to the second question and check the question first, and then come down to get the result. Okay, and in this case, in this exercise, we are just going to calculate the partial kind of derivation of a loss function. And no matter what is the loss function, you can just calculate the derivation easily in PyTorch. But here we want to define some variables manually, and then we initialize them and also calculate the loss function, and at the end, just by 1 line of code, calculate the partial derivation, which you can access for those variables using the grad attribute. So we will see the result here. Okay, solution number 2. So for this question, we first define our variable, or we can say that they are just our weights if we want to calculate the parameters that can be tuned and can be learned. So as it was presented in the question, you can see that W is just a tensor, but we mentioned the D type, and also we want this variable to be learnable. So we use required grad is equal to 2, and the device is just CPU. No matter, if you want, you can just say CUDA again. CPU is fine right now. We define all of our 4 variables: the weight, the bias, the input, and the output, something like this. And for the input and output, you can see that there is no enough defining it to be learnable, because we don't need them to learn something. So in this case, it must be kind of false, or just not mentioning anything. If you don't want, you don't need to set the parameter here. If you want, you can just say that I don't want it to learn anything. So the required grad must be false. And pretty easy, just calculate the loss function again. We use the W, X, and B. There are weights, input, and bias to calculate the output, which is Y hat. And with the Y hat, we have the loss value here. But because it is a the output of this formula is going to be a tensor, but the loss function, in order to be calculated by PyTorch, it must be just a single. It's a 0-dimensional or a scalar, or just simply a value. So I need to calculate the summation over the whole output tensor, and it is just going to be a value. And when I have it with this loss value, it's better to say it must be a PyTorch tensor. And also when I use backward method here, I can calculate the derivation. And then when I have it, you can see the initial values here for W and B. And then you can see that they are kind of updated or the partial derivation is calculated. They are not updated because there is another step for it. But the partial derivations for this loss value is calculated and saved inside each of the variables. In this case, W, it has the parameter set required grad is equal to true. But for the, I don't know, for X and Y, we don't have it. So in this case, the grad value is not 0 for W and B. As you can see that the shape is exactly the same shape as the defined or initial values. And then for the X grad, because we don't have required grad, so it is none. For the Y, it is the same because they don't have it. And also I can run the grad function, which you can see some backward because the last operation on this formula was just calculating the summation. That's why it shows the last operation, but it's like a backward version. So you can see that summation, and then I don't know, it could be multiplication, and also it could be inside the reverse version of this formula. It is all saved inside the grad function, but the last one is this one. Okay. And here, if you don't want to use the sum function on the top of the formula, you can just specify the shape here, that I want to calculate the loss function, but this is the shape of the L, but it must be torched at once. So when you don't have L in a scalar version and it is a tensor, you just need to mention the shape in this format. You say torched at once, and for each dimension, you just print it out for you. So it is going to be something. Oh, I calculated it twice that second. So now you can see that it is a vector of values which are 1 and in shape of the output loss value or loss tensor. But it's easier to just always calculate the sum or mean, I don't know, whenever that you, whatever that you prefer, and then at the end give it to the L dot backward method. And also, I think I have something like 15 minutes to cover exercise 3. And okay, so for this exercise, we are going, as we did it for the W and B, for the PyTorch models, we have, I don't know, millions of parameters like that, like W and B inside. So in the pre-trained models, like which are well known, like ResNet 50 or I don't know, other models that they have been trained before and the weights are provided, we can use these pre-trained versions and just train another or fine-tune another model for our specific task. We call it transfer learning when we use a pre-trained model, and it is just the same. But sometimes we don't want to change the parameters of the model. In this case, we can freeze them because by default, the required grad for all of those parameters are true. So they are trainable, but we don't want to change them. We want to use the feature extractor to extract the features, and we don't want them to be trained. So we go through the parameters one by one using the for loop, because we have the method parameters for the defined pre-trained models in Torch Vision. For other, I know that for other models that is defined manually and the weights are presented, we can use the same thing. So all the time you just say for param in model.parameters, this param that required grad is equal to false. This way we freeze the model, and with freezing the model, they are not going to be trained. So as we saw here for X, their grad value would be always none. Okay. And then we are going just to try to calculate the output exactly like we did before. But in this case, we don't have that formula. The formula is just my model. Give it the image and then calculate the output. So let's give it a try and then check the result. So as you saw before, we define the model and then we freeze all the parameters not to be trained anymore. And then we define the image like we did before. And another point is that here we need to say that how many images do we have. You know that this is just the dimension of the images. And here we have the batch size. It is just say that I have one image of shape 3 by 224. Nothing special. Just for the torch vision models, we need to have another extra dimension, which is my batch dimension. And then give it to the model, which is like before. Just calculate the output for this image, for the input image, and then I have it in the y-hat. But because we don't have the y, we want to just randomly define something like, I don't know. I know that the output y-hat shape is 100, but in order to specifically define y for different types of outputs, we just used zero-like function in PyTorch, method in PyTorch to have a vector of 0 and then make one of those vector values to be 1. So this is going to be my class label for the class, for example, 3. For the class 3, it is 1, and for the rest of them, it is 0. And then I calculate the loss function here. The loss function is just y minus y-hat and then square. And calculate the summation to have a single value, and I use loss.backward. So let me can run this enough code. So it is going to download the model, takes time. And then so actually the size is going to be just the size of the parameters that are saved for this model. And then I calculated the output. If you want to see the shape, let's say it is shape. You can see that it is a vector, kind of a vector, but in 2D shape, and I have 1,000 classes. So I just make the same thing. As you can see here, print shape. But it's going to be my true labels. It is the same shape, but I just made one of the classes to be 1 and the rest of them are 0. But I have probabilities inside y-hat. And in this case, let me create another cell here and then print. I don't know what is the values. Something. I don't want to go through the whole parameters, so just something like this for the first one, or maybe a few of them. Okay. Easier. Okay. So you can see I printed the grad value for 10 of these values from, I don't know, parameter 0 to parameter 9. And then it is, they are all none. It means that the model is freezed. So if I want to do the same, I just need to just unfreeze the parameters again. I can freeze and unfreeze them. And then here, I'm just going to copy and paste this cell right here. Again, I have lost the trackboard. Oh, no, not this one. This one. Print those parameters again. Okay, so in this case, I could just, instead of printing the grad, I can, because they are big tensors and they are all the shape of the parameters inside the model. So I just print the shape. So you can see that they are not none anymore, and they are just, this is the weight, this is the bias weight. I don't know, maybe it is bias or something, but these are the parameters that are inside the model. And then you can see that they have the same shape and they are not none anymore. So whenever you want to use the transfer learning, usually we freeze a part of the model, which is our backbone, or which is our the other name is feature extractor, and then based on that one, we can train a model for our specific task, and after that we can train a part of the model or freeze the whole model just to prediction for prediction. Oh, okay. I think I'm done. And if you have any question, you can still ask.
Thank you so much, Leon. Like, yeah, it was very nice to follow, and you gave really nice explanations.
Yeah,
So yeah, I think we have like 5 minutes for questions. So if anyone has a question, they can, the floor is up. For questions. Yeah.
I can't see any question in the chat.
Yeah, no, me either. Okay. So I guess at this point we can end it. If no one else has questions, like you guys, you can type it in the chat. You can raise your hand if you want. Yeah. Okay. So just thank you. So yeah, see you guys. So I think like the seminar is beginning in 30 minutes. So like you guys will have the seminars. And then you'll see Eugene and the rest of the team. Once again, I want to thank the mentors for preparing the assignment, and I want to thank Kehan for like just coming in and like saving the tutorial session. And with that, we can end the session. Thank you.
Okay, thank you. Have a good day. Bye.
Bye.